All right, so our new lessons here on exponential functions combines three sections, crams them all together, and whenever you cram those three together, of course, it puts the fun in exponential functions. All right, so our four gargantuan objectives for today, being able to define and graph these things called exponential functions, whether it's exponential growth or exponential decay. Number two, model real-world applications with exponential functions. So an example would be like money or population often have exponential equations in them. Number three, to compute compound interest. Interest is that stuff that you get for like investing money, give you some interest back, or maybe you borrow money and so you have to pay them for it. It's called interest. And then finally, number four, we have this new irrational number called e, and it's going to be basically everything that came above it, objective 1, 2, and 3, using that e. So define what that e is all about and use it as the base of an exponential function. So we were talking about like applications, or I was anyway, of exponential functions, and population growth is often exponential. So here we are on objective 1 slide, being able to define and graph exponential growth and decay functions. And in the picture, of course, you got a T-Rex. He's trying to graph an exponential function. And I don't know, something happened with the dinosaur population. Something happened. Okay, so if you look at this graph, it's kind of broken right there where he dropped his marker. He's pretty sad about it. That graph is supposed to look very similar to what we have over here in this flipping math logo. All right, and that's pretty much what it is it's an exponential function. So here's a definition of an exponential function. So we're going to write it with a base b, and b, I'm going to put some constraints on it. First of all, b has got to be bigger than 0, and it cannot be 1. So our exponential function is f of x is equal b to the x. So notice where that variable is. The variable is the exponent. The b would just be a number. Okay, so the reason why it cannot be 1 is because if it was 1, then you plug 1 in there, you just basically have 1 to the x power, which is just y equals 1, and that's not exponential, that's just 1. It's constant. Also, I can't have it being negative, because if it was negative, then if you're taking powers of a negative number, sometimes it bounces back and forth between positive and negative if it's an even power or an odd power. And then what if it's like fractions? What if it's like to the 1/2 power? Then you're bouncing back and forth between real and imaginary. So it's just kind of a headache, so we say, let's just make it positive. Okay. So let's talk about the difference between a power function and an exponential function. So what we've looked at before is something like x squared, where x is the variable, it's the base, and the exponent was always the same. So now we're kind of reversing that. Now 2 is the base and x is the exponent. Let's just compare those things. So like which one gets faster? So this is just a matter of just plugging numbers into the formulas like this. Magic. And so if you just look at the numbers right up front, when you have the quadratic, the x squared, when you plug in 1, you get 1, but in the exponential you get 2. If you plug in 2, in both cases you get 4, and if you plug in 3, you get a 9 on the x squared and an 8 on the other one. So they're pretty close to each other, but look what happens after the 4th power. This one, they're exactly the same, and then everything looks vastly different, and the exponential starts getting bigger and bigger and bigger faster than that parabola does. So let's just look at it on the graphs there so that you can see it. Okay, so that totally covered up my head, but that's okay. So take a look at this graph. So this first one is just the parabola. It's basically half of the parabola. And then here is the exponential one. So the exponential one is the red one, and you can see that it matches up at a couple of points, but that's about it. And then past this point, that exponential is going to grow faster and faster and faster. Okay, so let's do some actual graphing without a calculator here. So the first one we're going to graph is f of x, or y, equals 2 to the x. So we're just basically doing what we saw on that previous example there, that I'm just taking powers of 2. And so whenever you do this on your own, I wouldn't expect you to make a table of values. But it might be healthy to look at one, or just to see what exactly you're trying to do in your head whenever you go to graph this.
Let me switch back down here to purple, keep it all consistent. So x versus my y-coordinate is going to be 2 to the x. So let's just start from negative 3 and go to positive 3. Negative 3, negative 2, negative 1, 0. Oh, gotta make that bigger. And 1, 2, and 3.
Okay, so if I put in negative 3 in for the power on 2, it's 2 to the negative 3 power. The negative makes reciprocal, and 2 to the third is 8. So it's the reciprocal of 8, which is 1/8. Okay, if I plug in negative 2, the negative is just going to make it flip upside down, and 2 squared is 4, so it's 1/4. Okay, if I plug in negative 1, that's just a reciprocal of 2, which is half. If I plug in 0, anything to the 0 power except 0 is equal to 1. Plug in 1, of course it's 2. 2 to the second power, it's 4. 2 to the third power, it's 8. Okay. Obviously, whenever you go to graph this, there's no way you're going to get this kind of accuracy. You're not going to be able to find those points on the graph. So you just need maybe a half. You could start there with a half. On Sketchpad, though, I went ahead and got as close as I possibly could. So there's 1/8 right there. It's exactly right there in that location. And then you have your 1/4 at negative 2, and then a half, and 1, 2, 4, and 8, and then connect it to make your exponential graph. Okay, now again, whenever you go to graph this, all I would expect you to do is maybe start at that negative 1 power, and that's just the reciprocal. So if you got 2, take the reciprocal of that, it's a half, and I'm going to start there. Now I'm just taking powers of 2, so 1, 2, 4, and 8, and that's enough to make your little graph. Now let me ask you a question. This graph that's getting close to the x-axis, is it ever going to pass it? Is it going to go to the other side of the x-axis? Is it ever going to be negative? The answer is no. So it's never going to cross that line. And a line that you never cross on a graph, but you get closer and closer and closer to, is called asymptote. So this graph has a horizontal asymptote at the x-axis. Okay, so let's look at number 2. So on number 2, I'm not going to bother with the table of values. I'm just going to talk it through just like I'd expect you to do in your head. So for example, on the next one, if I plugged in negative 3, I'd get 1/27. I wouldn't expect you to graph that one. I wouldn't expect you to graph 1/9 for the next one. And then you have 1/3. Okay, so I got 1/3. That's pretty easy. And then 1 at the 0 power, and then 3 at the first power, 9 at the second power, but the rest of it's going to be off the graph, and there you see it. Okay, so if you compare these two graphs, of course the one that's in green, the one with a larger base, it is steeper. Okay, it's going to get bigger faster, but on the other side of the x-axis, it's actually down below it, right? It's down below the purple graph. Okay, so finally let's look at 4 to the x. So same thing, I'm just taking powers of 4. So on this one, I would have started at the, let's say I started at 3, so that's 1/64. Plot that, yes. And then 1/16, and then 1/4. Even 1/4 is pretty tiny, right, trying to graph that sucker. And then 0 to the first power is 4, to the second power is 16. I don't have enough room in order to graph it, so that's what I've got. All right, so there's, without a calculator, not too much trouble to graph some of these exponential equations. Okay, so let's flip this over and actually look at now the base being a half. Now let me go back over here for just a second. Notice that every single one of these is getting bigger. Every single one of these is growing. This is examples of exponential growth. Let's see if the same thing is going to happen over here on exercise 3. So I want to do the same thing. I want to take powers of a half.
So I just want to walk you through that again, because this will be the first time that you see it. So x and 1/2 to the x power. And let's go negative 3, negative 2, negative 1, 0, 1, 2, and 3.
Okay, if I stick in negative 3, The negative part makes it reciprocal. So instead of a half, you have 2. Now to the third power makes it 8. To the negative 2 power, the negative makes it reciprocal. So it was 1/2. Now it's going to be 2 raised to the second power. It's 4. Negative 1, so I'm just taking the reciprocal, it's 2. Anything to the 0 power is going to be 1. To the first power, it's a half. And then I've got a fourth and then an eighth. Then I want to just start graphing those points left to right. So there's the first one, -3/8, -2, 4, -1, 2, and so on. And at this point, that's where I'd expect you to stop and then go ahead and draw your graph. But I had the ability, I had the technology to go ahead and do more of those points.
So if I look at the second one then, 1/3 is the base taken powers of the 3. If I take 1/3 to the -3 power, flips it over, and it's 27. That's going to be too big. It's off the graph. So the next one is the -2 power. Flips it over. I get 9. And then 3, 1, a third, a ninth, and so on. And there's my graph. Are these getting bigger, moving from left to right? As x gets bigger and bigger, are these things increasing? Let's look at the last one here. The last one, 1/4. I wouldn't be able to do the -3 power because that would be too big. The -2 power is going to be 16. That's too big. So then the first one that I'm going to have is the -1st power, which is 4. And then 0. Whoops. 1/4, and so on. And I would expect just those 3 points whenever you try to graph that for me. And there you go. So these things are not growing exponentially. These things are decaying exponentially. So these are graphs that display exponential decay.
So let's put those things together right here in this next slide. So looking at the definition that we saw before for the exponential function, I just took the f of x out, put a y in it, a times b raised to the x power. So if b, the base right there, is bigger than 1, like the first exercise we looked at, it was a 2, a 3, and a 4, then this thing is going to get bigger and bigger and bigger. It's going to be exponential growth. And so your graph is going to look like that purple thing right there. Okay, very similar to the flipping math logo, like right up above my head. Okay, and the b is the growth factor. It's how much it's growing by each time you take powers. Okay, now if the b is a fraction, if it's a fraction between 0 and 1, then this thing is going to get smaller and smaller. I'm taking half of something, and then I take half of that, and then I take half of that. It just keeps getting smaller and smaller. This is an example of exponential decay. And that's the green graph that's right there. It's just getting smaller and smaller and smaller as x gets bigger. And b, just like before, the b is called the decay factor. It's what you're decreasing by each time you take powers of that. And remember, right there at the x-axis, you have yourself a horizontal asymptote. So let's look at some key parts of those graphs, maybe something to write down. So here's your graphs again for an exponential growth function. I know these are growth functions because the b value, the base, is bigger than 1. The domain, well, I can stick anything in there I want to. It's all real numbers. The range, since I have a horizontal asymptote at the x-axis, is everything bigger than 0. So I don't include 0, but I go up to infinity. Horizontal asymptote at the x-axis, or y equals 0. This thing is always increasing, which gives it its name, a growth function. And it's continuous. Continuous just means that whenever you draw it, you don't have to lift your pencil off of the paper, off of the graph paper. And then finally, it's a one-to-one function. Remember what that means is that it passes both the vertical and the horizontal line test. If it passes the vertical, it's a function. If it passes the horizontal, that means its inverse is a function. And sneak peek, that's right up above my head right up there. The inverse of an exponential, since it does exist, is called a logarithm. Okay, so looking at the decay function, everything, if you look over here on the left-hand side, everything is almost the same. The domain is still the same. The range is still the same. Horizontal asymptote in the same location, except for now this is a decreasing function from left to right, and we call it an exponential decay. Okay,